Okay, so last time we started looking at a low-energy effective field theory of gravity. In that case, we looked at loops of heavy fields that may be present in the UV, whatever this UV is. It may be a partial UV completion. And we're trying to understand what the connection between the effect of these heavy fields on the low-energy effective field theory is. In the case of the cosmological constant, we had a look at various Feynman diagrams, expanding the metric in this form, where the real degrees of freedom for gravity are living inside here. And then we saw how when we perform this decomposition and look at the endpoint function for any type of H, where we could reconstruct what would be a contribution to the cosmological constant that would scale like the mass of the field that you integrate out to the power 4, and then we had some renormalization of the Planck scale effectively, and also renormalization of other operators that come into the low energy effective field theory for gravity. So what I'm gonna start doing today is perform an exact one loop effective action for the cosmological constant at low energy. So we see that we don't need to do this separation of the metric. And then I'm sorry, I'm not gonna do that for all other operators, but hopefully once you see the techniques, you can convince yourself how you would generate other type of operators in the low energy effective field theory for gravity. So just as an example, and that's the same example we did last time, in my UV, or partial UV, so that's not a completion of gravity, it's just a partial UV. Let's imagine that my field content in this case is just gravity and one heavy scalar field. So I don't have any light scalar field, I don't have any light itself, for instance, I don't have photons, but that's just for simplicity, okay? It's just as an example. So in this case I have GR, and let me put the square root minus G being present in here. And then I have a scalar field, which is d phi squared, and I'll just give it a mass. I could, in principle, give it an arbitrary potential. It doesn't matter too much. But for simplicity, let me just give it a mass in this form. And so the coupling between that scalar field and gravity comes in through the inverse metric living here and comes in through the determinant of the metric in there. Now, I want to determine what the effect one loop is from integrating out this scalar field in this sense. And so let me work in Euclidean space to start with, and I will go back to Lorentzian space afterwards, just by continuation. So working in Euclidean. Oh, yes, thank you. Yeah, that's rather crucial, huh? Thank you. Okay, gravity is implicit. Working in Euclidean, so I'll just take my time and make weak rotation. That's just so that I don't need to worry about the factor of i's. I'm not very good with those. And so I'll write my low energy effective action at one loop. So this is for my matter loops. And so this at low energy will only be an action which depends on the metric. I'm integrating out the massive scalar field, so this will only depend on the metric itself. And sorry, it's a bit hard. This is all in exponential, right? And then this is equal to the integration of my massive scalar field, which has a mass larger than the cutoff of my low energy effective field theory. And then to leading order, I can do an expansion about a vacuum. Let's here phi is 0 is a consistent vacuum. Stable vacuum. If you're unhappy with that, then we already have problems at this stage. So let me imagine this is the case. And then I can do a Taylor expansion to leading order. This will be my Taylor expansion over the scalar field. And not to confuse myself, I'm going to evaluate this at G bar. So this depends on G. And let me put a G bar here, just so I don't confuse myself. And this I evaluated in my vacuum. In this case, I consider it to be 0. Of course, you can generalize that and consider a vacuum, which is not trivial. But let me, with that loss of generality, just consider that here, phi bar. And then it has high order corrections, but to leading order, let me just consider that. And that looks very much like a Gaussian integral. So this here now no longer depends on the field. This is quadratic on your field. And just as a reminder, if I have a Gaussian integral of e to the minus a half, and a matrix Aij, xi, xj, I integrate out in an n-dimensional space. So let me imagine this is a matrix, an n times n matrix with vectors xi, xj in an n-dimensional space. Then this Gaussian integral will be 1 over the square root of the determinant of this matrix A. And then there's some factors of 2 pi, which I'm not going to worry too much about. So hopefully you've seen that before. Yeah. So now I can do exactly the same thing here. If I wanted to be not as lazy as I am, I would really split my field phi. Instead of saying it's just it's a field, I will split it into its values at different location in space and in time. Now time is Euclidean, so I just have space, and then I will characterize that as an n-dimensional vector in the same way. But I'm lazy, so let me not do that and just get to the answer. The equivalent of this will be the determinant of this matrix. So this is my matrix here, and that will come in the denominator. So at the level of, well, let me write it like this. This will come in at 1 over square root the determinant of d square s over d phi squared at phi is 0, and the metric is G bar in this form. That's the square root of the determinant. And let me be a little bit fast with the factor of 2 pi. I don't want to focus on that. And so that tells me that at one loop effective action from the matter loops when I put that back in terms of something that will come in the exponential, I will get a log. So this is equal to a half of the log. The half is coming from the square root. I have a minus sign here, which corresponds to the 1 over it. And I have the determinant of this functional. And this is, again, in my vacuum here, I consider phi 0, and G is G bar. I'll just write it differently, not to confuse myself between the different G's. But it doesn't matter, that aspect, too much. Okay, so now you've probably seen that the log of the debt of a matrix, let me call it A because I had a matrix A. This is the same thing as the trace of, the trace, of the log of the matrix. Have you seen that? Yeah, you can do that with the eigenvalues if you want to. Okay, so I'll rewrite this in terms of the trace, and the trace in this case corresponds just to the sum of the eigenvalues, and I'll work in Fourier space to evaluate them. So these are the matter loops. is my effective action, depending in the IR, just depending on the metric. And so this is equal to a half the trace of the log of this functional. Okay, let me not rewrite everything else. So now let me work in Fourier space. I want to rewrite this in terms of its eigenvalues. In Fourier space, what I have is d square s over d phi squared. This is equal to a half g bar AB Ka Kb plus m squared. So this thing, now I'll have the Lagrangian really, is equal to a half, and then the trace corresponds to the sum of all the eigenvalues. Here that corresponds to the integration of the momenta. There's some factors of 2 pi, but I've been very quick about those, so let me not worry too much about the factors of 2 pi. And then we have the log of this half g bar AB Ka Kb plus m squared. And at this level, I can perform this integral by changing variables, and this is where I'm going to be working just to first order in curvature, or to 0th order in curvature, which is the cosmological constant. I'm going to change variables in my integral. So I have an integral over k, and I'm going to go to a new k. So my Ka will go to Ik tilde A, which is such that G bar AB Ka Kb goes to delta AB. Remember, I'm in Euclidean. K tilde A, K tilde B. Plus derivative corrections, well, on the metric. So because I'm only interested in the effect on the cosmological constant, for now, you don't need to, but just for simplicity here, I can consider a case where the metric itself is constant, and I can perform this change of variable. If you want to be more sophisticated, then really when you try performing this change of variable, you will include some contribution on the metric itself. And these are going to be the curvature corrections in your effective field theory, which I don't want to worry about here. So the measure of d4k in this case gives you the determinant of G times the measure of k tilde. And I do that so that at this level of the integral, I get something which no longer depends on the metric. It will depend on corrections, but those will be dealt with if you were looking at curvature corrections. And all the dependence on the metric is now factorized inside the integral. So you'll have your one loop effective action is equal to that G bar over 2. And then you have a number here, which is d4 k tilde over your factors of 2 pi to the 4, and then the log of delta AB k tilde A k tilde B plus m squared. In this case, plus corrections. In this case, this integral diverges in 4 dimensions. We need to regularize it I suggest doing dimensional regularization. And when you do that, this thing will give you some log of the difference between the number of dimensions and 4. And the only scale present in the system at the level of the integral, this is something which is dimension 4 in scale. And the only scale it can depend on is what? The only physical scale that is present, m, exactly. So this will scale like m to the 4. There's nothing else it can depend on. So this is the scaling. It does diverge. So to absorb the divergences, you're going to need to include some counter terms. But overall, the scale of this term goes like m to the 4. And then this is similar to what we had before, yesterday, when we split the metric into, for instance, Minkowski, and then your degrees of freedom hidden in H mu nu. And we looked at diagram by diagram. We were getting corrections for the cosmological constant that would scale like the mass of the scalar field to the 4. This is the exact same result. Yeah? Yeah, G bar, it's looking at a consistent vacuum. Yeah, yeah, yeah. Oh, here you're worried about the Lorentz or the Claudian. Yeah, you can do it. This you can do. For the scalar field itself, you can do. They are just the momentum of the scalar field. You don't assume any particular symmetry, right? You're here in a Claudian. Now you're worried about whatever symmetry is present in there, but that's kind of captured precisely by this wave rotation. Yeah. Okay. So. Okay, so more generically, what I should say before I go into more generically, this was an example. Can you see me here? Not really. Let's see. Okay, so this was an example for one scalar field of mass m. It leads to a contribution to the IR. Here we're dealing in Euclidean, but we can go back into Lorentzian now. That would include square root minus g of the mass of the scalar field that you integrate out. Now, typically you hear the cosmological constant problem as a problem at the Planck scale, where people say there's contribution from the vacuum energy that scale like the Planck scale. This is only if you consider that there will be fields with masses all the way up to the Planck scale that will contribute to the vacuum energy. I don't know if that's the case. What I do know is that a Higgs field exists, and so naively I should at least put the mass of the Higgs here. This is something I do know. But if you consider, now let me just do n bosons of mass m, it will scale roughly like square root minus g, the number of field, n to the 4. So you can do the same procedure. You'll have n of them, and you'll see that you just sum them up, and you'll have that. Now, if you have fermions, if you have, let me just say, one fermion of mass m, you've probably done this Gaussian integral before with, where is it? Here. If you have spinor statistics for your matrix, you get, instead of getting the 1 over square root of the determinant, you just get the square root of the determinant. So that put back in terms of the exponential, it gives you the opposite sign. And so for any half integer spin particle, you will get a minus contribution. Precisely which number here you have will depend on the precise spin, but if it's half integer, it's negative. If it's integer, it's positive. And so if you have supersymmetry, you will have a complete cancellation between all of your bosons and all of your fermions. And the net result will be exactly 0. Exactly the case. So it is possible there's a hidden sector out there which is not coupled to the standard model, which is weakly coupled, and that precisely cancels out all of the contributions that we see from the standard model. It is possible. I don't know. It needs to be it needs to be some type of very precise cancellation occurring. We don't know. What may happen is that you have supersymmetry up to some scale. So not the TV scale, we know that's not the case now, but maybe a little bit above the TV scale, you have supersymmetry all the way up to that scale. So when you integrate out all of the massive particles up to that scale, they cancel out exactly, and the left over to the cosmological constant are just the field under the breaking of the supersymmetry. But this is still too large for the cosmological constant that we're observing today. So at the very least, if you want, in that sense, supersymmetry to tackle the cosmological constant problem, you're still left with something which is TV scale, as opposed to something which is 10 to the 56, I think, orders of magnitude below. Okay, it's possible that there's other mechanisms that allow you to cancel each other. So my original plan was at this stage to go through different ways people had attempted to tackle the cosmological constant problem, including using massive gravity. But I'm running very much out of time, so I'm not going to talk about massive spin-to-field at all. And then if anyone is interested, I know there were some questions about VDVZ discontinuity or about the EFT of massive spin-to-field. If you're interested, come and see me after lunch, and I'm happy to have a little informal discussion, maybe in the other room or something. But just come and see me. So let me now continue with the EFT of gravity. So we've done that just for the cosmological constant. Let me just tell you what happens more generically. So you have a relation between your IR EFT and a UV EFT. So now let me imagine generically your SUV includes, I'm back to Lorentzian now, some curvature, standard GR in the UV, and then you have your light field. You possibly have some heavy fields. That could, in principle, couple to some light fields, and you have some counterterms that need to be present to absorb the divergences that will happen when you flow down into the IR. And those counterterms, in principle, I don't know what they are, but they can take any local form consistent with the symmetry. So here we have covariance as a symmetry. It's possible you have other symmetries related to your field content, but generically I don't know what those would be. But they could be your cosmological constant in UV, and it's possible that this cosmological constant in UV will be there precisely as to cancel the contribution from every massive particles, massive loops that you will integrate out. This is a fine-tuning, but it's in principle possible. Then you'll have some contributions to, let me write them, R squared UV, all of the Riemann square contributions. So let me just write one of them here. Symbolically, you could have that. And then all of your Riemann cube contributions, R cube, mu, nu, alpha, beta, etc. So all the terms consistent with the symmetry. And you can have derivatives acting on those. And then in the IR, you'll have something which is similar, and you'll have a flow of your Wilsonian coefficients. So you have your cosmological constant in the IR, which we know is now given by what it is in the UV, plus the contribution of the matter loops that you have integrated out. Then you have your standard gravity. You have just the contributions from the light fields themselves. And let me add. So you have, for instance, those types of terms coming in, and similarly. So these are all type of Riemann contractions. In principle, you also have derivatives acting on those, but up to this order, you can always rewrite them in terms of Riemann as well. And so we know that, for instance, the connection between the IR cosmological constant and that of the UV is this plus a given number times the number of matter loops fields that you integrate out. So not the number of loops, the number of fields that you integrate out at one loop. For the Planck scale itself, we know that it's the original one in the UV plus another number times n, the scale m squared. We've seen that scale coming in last time. And now for the relevant operators, we have some flow from the UV as well, which here just goes like a number times n. And hopefully you see the pattern here. So this will go like m squared, for instance. So for this operator here, you see that you are typically dominated by the more massive field that you integrate out. But as you go to the more and more irrelevant operators, you're dominated by the lightest field that you integrate out. And so typically, your intuition would be that the operators, the Wilsonian coefficients of the operators that you have in the EIR will be dominated by the scale, by the cutoff of UFT, by the scale at which the lightest field that you have integrated out to get your UFT. So often what you will see in here is just that contribution, but of course, who is to know that there could be a bigger contribution coming from here? We don't know, but typically the scaling that you will see is that type of one there. So these are for loops, integrating out loops of particles of spin less than 2. So you can do it for, we've done it for a scalar, you can do it for a vector, you can do for spin half or spin 3/2. I'll talk very briefly about higher spin in a second, but let me just talk a little bit about what happens here. For the cosmological constant itself, we've seen that this number there, or argued that the number here depends on the statistic of the field you integrate out. If you have supersymmetry, in the end, you just end up 0. So it's positive if you have bosons and negative if you have fermions. And that's the case for this number here as well. So this number is actually 0 if you have supersymmetry. And that's the case here as well. Now, something which is not necessarily obvious, but we will see tomorrow, is that the number that comes in here and the number that comes in here for the Weil, if I focus on the Weil tensor that comes in there, And some of them that comes in at higher order as well are always positive, and these are coming from positive energy type of theorem from unitarity. So here, that number is positive for instance, the Weyl square term. And then you may say, well, that's a good insight, that's good indication that the Wilsonian coefficient itself should be positive, but that's not necessarily the case. And we'll talk more about it tomorrow. But definitely this difference between the UV and AR is always going to need to be positive, and the same thing in here. And that's what led to the species bound that we discussed about yesterday. So in principle, this could be smaller than the Planck scale, but however you integrate out massive loops of other fields, it has to be such that you don't integrate too many of them. So there's a bound on the number of species that you can have, even on the dark sector. So with this scaling in mind, what often people do is assume that you're dominated by the lightest fields. And so if you're considering a low energy EFT, for which the Wilsonian coefficients are dominated by the lightest fields you have integrated out, the scale that would capture all of the irrelevant operators would be the scale M. So typically, we consider for the integration of spin less than 2 fields, in cases where we can do it explicitly, and that has been done in the literature explicitly to quite a high order, you get your IR, which is d for x square minus g. I'm not quite sure what to do with the cosmological constant, because clearly it cannot be of the high order. So let me put an IR here, but solving it is not something I'm going to do it. So this is your cosmological constant. And then you have the Planck scale, which you can't touch. This is fixed by our knowledge of what the Planck scale should be. And you have an infinite number of operators, which are captured by Wilsonian coefficients that go like, let me say those are now dimensionless, and I can have arbitrary number of derivatives acting on arbitrary number of contractions of the Riemann tensor. And this goes like the scale m to n plus p minus 4. And so you have all of those irrelevant operators for which this is larger than 1. So for 2 n plus p minus 4 larger or equal than 1. Actually, you can take 0. The R square will be living in there. So in deriving this scaling, we're considering integrating loops of matter fields. So we considered a scalar field, but you could do a vector field, you can do things like that. So these are loops level, but if you consider higher spin, in principle, you can consider your graviton h mu nu, h alpha beta, coupling to a higher spin, mu nu alpha beta, and then you have some other h coming in here, h coming in there. And in principle, you could consider those type of tree-level contributions. They will contribute to operators in your IR EFT at tree level already if you have higher spin. If you have lower spin, you can try, and they will never affect the graviton itself because they don't have at tree level, because they are too low spin capture any dynamics of the spin 2 field. But if you have high spin, that's okay. And if you have loops, that's okay, because hidden in the loop is a superposition of an infinite number of spin. So if you have higher spin, you can do it at tree level. And the fact that you do it at tree level, you kind of have some H-bar enhancement, one of H-bar enhancements as compared to what you would have had if you had done it at loop level. And so this H-bar is really captured in an enhancement in Planck scale. So this is for loop, as an explicit example. And then for tree of lower spin, you can do it explicitly in theory, for instance. And what you'll have is an enhancement as compared to the loop level by the Planck scale itself. So the scaling, I'm not going to integrate out a tree level, a higher spin, because it will be a little bit too much for us today. But let me forget about not be too explicit about the cosmological constant. The overall is scaled by a factor of the Planck scale compared to what you had before. So those were loop. And if I had tree of spin larger, particle spin larger or equal to 2, we have something that looks very similar here. With the contraction. We have the scale of the massive high spin you integrate out. But you have less suppression, or if you want, you have a Planck scale enhancement. So if you have two fields that you integrate out, one of lower spin, lower than 2, and one of spin higher than 2, 3 or more, at the same mass, for the irrelevant operators, the higher spin will give a dominant contribution. However, in practice, as soon as you have a higher spin mode, a massive higher spin field, to make it consistent, you need a whole tower of higher spin mode that come in, and that's to preserve unitarity. We'll discuss very briefly about that tomorrow. I'll mention where it comes in, but you really think that this is the setup of a real quantum gravity, the scale at which the higher spin kick in. So you may think of it as the string scale. You may think of it as something coming more fundamentally just from a higher spin states. But this is not something we're observing, for instance, at the TeV scale at the moment. So typically, you would expect to have lower spin states, which are lighter, and then the higher spin state to come in at a much, much higher mass, and therefore those ones are suppressed by the higher mass in which they come in. But these are in specific realizations. This is inspired by string theory, if you want, of higher spin contributions. This is inspired by performing some explicit loops calculations in models that we consider. But part of the goal of the effective field theory is to remain agnostic on what the precise completion is, because it could be something we haven't even thought of yet. And so in principle, when you write down your effective field theory, you should allow yourself to have any type of scaling between this one and that one without being too deterministic on what precise completion you want to have. Okay, so I have a few more minutes before in the last 15 minutes or so, I wanted to look at more generic effective field theories that include some coupling with other fields. Yes? Yes? Yes, yes. Yes, you'll have an infinite tower of higher spin state that have to come in. And I think it'll be easier if I explain that tomorrow, if I can, where it comes in. If you want to see why, you go to Green, Schwartz, and Witten, the first page. No, I think it's page number 2. And they do go through that. They do explain how as soon as you have a massive spin 2 or higher, you need a whole infinite tower of them to preserve unitarity. Because individually, all of them have a contribution to the amplitude that grows too fast. And so they need to tame each other through an infinite tower of them. Any truncation in the number of spin will lead to an amplitude that grows too fast. And so I can't quite see who is asking the question. But yeah, hi. Yeah. So I'll show you a bit more explicitly where you can sit tomorrow. And if I haven't answered your question, go to Greenshot and Witten, but otherwise ask me as well. But of course, Greenshot and Witten will give you the ultimate answer. Was there a question? No. Okay. So one thing I should... Last line here. Lambda IR. Yes, sorry. I don't know how to solve a cosmological constant. Let me just put that. Yeah. yeah. No, you're right. It has a different dimension. Yeah. Okay. Let me put it lambda IR over the Planck scale squared. I think that's more precise. Okay. So before I go into more generic EFTs, if I have time, I don't even know. I want to make a brief comment about Ostrogatsky instabilities, which I was meaning to talk about yesterday, and is a verified point for today. So in all of these higher derivative operators, and all of those operators here and there, the reason they were not originally, when GR is formulated, we say that GR is unique with a cosmological constant if we invoke the Lovelock theorem that requires no more than 2 derivatives, and we don't want more than 2 derivatives because otherwise they lead to Ostrogatsky type of instabilities, which we have gone through. And yet here, very happily, I write you down an effective field theory that includes an infinite number of operators, all of which will include higher derivatives. So the reason why we're not too worried about that is because it's a low energy effective field theory, and all of those operators should only be considered perturbatively. We're only allowing ourselves to look at energy scales which are well below the mass of the field that we integrate out. So this is an effective field theory consistent below the scale M. So whatever process you want to do, you may want to do things classically and look at black hole configurations. You can only allow yourself to look at those operators if the curvature is around the black hole is well below that scale. You may want to look at scattering amplitude. You can only do that in this EFT if you're considering processes for which the center of mass energy, for instance, is well below that scale. When you get close to that scale, then all of this infinite number of operators will start becoming important, and they should be resummed, and you know where they came, well, you don't necessarily, but you know that they came in from having integrated out heavier field. So when you get close to the mass of the field that you have integrated out, or when you get close to the cutoff of your effective field theory, you can't just get along with your effective field theory. You need to reintroduce back the dynamics, the macroscopic physics that come in at high energy. So this is only making sense perturbatively. The EFT operators should be treated perturbatively. And when you do that, there's no issue with the Ostrogatsky ghost. So to show you an example, it's easier for me to consider scalar field theory. You can do the same thing exactly in the case of gravity, but it's easier to think of it as a scalar field theory. So let's imagine you have an EFT for a scalar, which looks like this. And then you have maybe a higher order operator that involves higher derivatives. And then you may have something that goes like D, let me call it B, d mu phi cube. That goes like the scale, in this case, is m to the 5. And you have an infinite number of operators. I'm just specifying those two because it'll be easier for me to deal with a finite number of them. But in principle, you should write down all the infinite number of operators that come in. Now, there are operators like this. Clearly, when we were dealing with phrasing an EFT for a vector field and then for a spin-2 field, we were saying that we can't have the theory for the field at quadratic order just to start with this one without the standard kinetic term, because this would lead to a ghost. Here the situation is slightly different because we have our standard kinetic term, just like we have the standard kinetic term for the gravitational waves, spin-2 field, dynamical degrees of freedom hidden in here. And this is an irrelevant operator that we add perturbatively on top of it, and we can only consider its effect when it's small as compared to the standard dynamics. In this particular case, this one can be removed by a field redefinition. Actually, if you have an effective field theory of this form, any operator which would be 0 on shell at the leading order, here the equation of motion on shell in this particular case is just 0. Any operator which be 0 on shell can be removed by a field redefinition. In this case, it's rather simple. You can say phi goes to a new phi tilde, which is equal to phi. Which one is it? It's plus a half a box phi tilde of m squared. So you can write that plus other. And perturbatively, this field redefinition, you'll have a contribution from here, which will be L of phi bar tilde is equal to, the first term is your standard one from here. Sorry, I meant that. Let me write it like this. Yeah. The second one, you have a cross term from here, which is plus a half. No, it's plus 1a. And then from here you have box phi tilde of m squared. Actually, I think it should be a minus. It doesn't matter too much. So that's a minus here. And then from here, you have the plus a box phi tilde squared of m squared. And then you have higher order corrections. But those two things cancel out. So anything which is on shell at leading order, which is proportional to something which is on shell at leading order, would vanish on shell. You can remove by a field redefinition. Now, if you had a mass term, m squared phi squared, this doesn't vanish. You have your m squared phi squared there. But the leftover term will be itself something which is lower order. So you'll end up with something that goes, sorry, I think it's like that, m squared, and you'll have your box phi tilde, and then you'll have this other m squared, and that would be suppressed as compared to that. So any operator like this can be removed by a field redefinition. Here, I cannot remove it exactly by a field redefinition, so this will remain a generally higher derivative operator term, but the aim of the game is to make sure that it's no more than 2 order in derivative in time derivative. And you can allow yourself for higher space derivatives. And that I can always do at the price of performing a field redefinition which is not Lorentz invariant. So I'm going to manifestly split my space and my time, but that's okay. I'm going to commit to a slicing in time. And then I can write this EFT in a way which is manifestly second order in derivative at the level of time. And so it has no Ostrogatsky instability at the price of pushing other effect to higher order, But when you're dealing with an EFT, you do that perturbatively, and so as you go to higher and higher order, things become more and more suppressed, and you can always do it perturbatively to any order you want. And when the perturbative approach doesn't work, you shouldn't be using this EFT at all. So let me just show you quickly, and you can do it when you have time more slowly. Let's imagine now we have, I'm just going to focus on that operator square, which is plus b d mu phi cube over the scale m to the 5. So this has higher derivative, and I can't remove it with a Fourier definition, but I want to think of it perturbatively. So there's other higher dp phi and m to some scaling that come in here. So this is just one term in this infinite expansion. So this, if I split my space and time, let me just work in 2D. So one space and one time, just to be simpler. So I have gradients and I have time derivatives. Here I have higher time derivatives that seem to be present, but when I treat them perturbatively, I don't need to worry about them. So you have a term like this, which will lead to terms with 4 derivatives at the level of the equations of motion. You have a term that goes like that, which will lead to 3 derivatives at the level of the equation of motion. When I say derivatives now, it's really time derivatives. And the gradients, I don't need to worry too much about. Okay, so I split my space and time in this form, and you have your higher order operators that come in. So those terms seem to be bad. Those terms seem to be bad. Those ones are okay. I don't need to worry too much about those ones because they remain second order in derivatives at the level of the equations of motion. So to deal with them, I can perform again a Fourier definition, which now will involve some splitting of space and time. And in this case, you can check. You can do something like that, plus phi double prime minus 3 phi dot prime squared. Okay, it's very simple. Just check it, and then you have some higher order contribution coming into your field by definition if you want to remove them at higher order. And that, in terms of your new field, your EFT will have the first term will be the same. This Fourier definition is going to mix the kinetic term with those modification and then be there as precisely as to cancel this term and that term, and at the end of the day what you get is b over m5 phi double prime squared box phi plus higher term. So now this is manifestly second order in time derivative. You are fine at this level. You could even further, you have a box here which you can further remove with a Fourier definition, and what you'll get is a term at higher order that would involve phi double prime squared box phi double prime squared over the scale m to the 10. And this is really where your operator stands out. This is still second order in time derivative. So perturbatively you can do that because you push anything to higher order. If you wanted to say it in another way, the Ostrogatsky ghost associated with that has a scale which is the scale of the cutoff, and therefore you cannot trust that you excite it. It's not the case that the presence of a new pole in your operator corresponds one by one to the new degrees of freedom that you should have included at high energy. There's not a one-to-one correspondence in this sense, but the fact that you have a new pole in a propagator, as we mentioned, at a scale m squared, indicates a failure of the EFT, and therefore tells you that you will need to include new degrees of freedom, the macroscopic physics to consider it. So if you have something like that, this corresponds to a box, and then I'm going to get the numbers wrong, but you have something like box minus m squared. It's not quite this, and this is always coming in with a negative sign. So if you have an operator with a box squared in addition to your standard kinetic term, you can split into the standard one plus corrections. And so there's something here. It's a good exercise to work out what is explicit decomposition. You see that you have a new propagator with a new pole, but the presence of this pole cannot be trusted because you need to have probe energy scales related to the cutoff of the FD to probe it. What it tells you is that you need to reintroduce your microscopic physics to describe what's going on there, and that will lead to additional degrees of freedom, but which are not captured exactly in the same way here. They're just captured differently. Okay, so I'll continue the rest tomorrow, and we'll try to make a bit more of a connection between these ideas of positive flow from the UV to the IR and how it can be used to constrain your low energy effective field theories of gravity.